happens sometime. Okay, so welcome to this next NSM course on scientific computing on GPUs with OpenACC. And I'm happy to see multiple of you joining multiple of NSM courses. Please keep up the enthusiasm. We have multiple interesting courses lined up. Um, yeah, so this particular course is going to be instructed by Durgajyoti Bishwas. We had conducted one OpenACC course last year, and Durgajyoti did very well in that course, and I felt that he is probably the right person. He also went ahead and did many more things than what was taught in the class. So Durgajyoti is probably the right person to take this second instance of OpenACC. And I'm delighted that he has agreed to our request of delivering this course. Durgajyoti is a PhD scholar in the Department of Physics at IIT Madras. His advisors are Vaibhav Madhok and Sayan Gupta. He primarily is interested in the area of complex networks and high-dimensional dynamical systems. He is also interested in learning about applications of HPC and parallel computing using API like OpenMP, OpenACC, etc. in physics simulations. He completed his MSc from IIT Madras and now currently towards the end of his PhD. He says that he's very passionate about programming and photography. So you can possibly ask both kinds of questions to Durgajyoti in this session. Over to you, Durgajyoti. Yeah, I think it's still muted, Dhruv.
Oh, okay. Now it's fine?
Yes, yes, great.
Okay, so thank you for the kind introduction, sir. I'll just share my slides and share my screen.
Yeah, screen is visible, yes.
Yeah, okay. The screen is visible, right?
Yes, the slides are visible now. Great.
Oh, okay. All right. So, welcome everyone to this course on scientific computing on GPUs with OpenACC. I'm Durgajyoti, and we will be having around 3 weeks of Saturdays and Sundays afternoon where we will discuss this topic. So, as sir said, I am a research scholar at the Department of Physics at IIT Madras, and my research work pertains to complex networks and dynamical system simulations, where I have found that there is a very nice potential application of HPC parallelization, and I typically use GPUs for my application in my research. As again sir said, my background is in physics, so I completed my undergraduate degree from St. Xavier's, Kolkata, and my master's from IIT Madras, and I'm doing my PhD now. You can reach me at my email at dhruvaJyoti98@gmail.com, and you can look up more details for my other research work on my website. Okay, so let's look at the objectives for this course. The primary objective is to learn about parallelization for a faster execution of our code. The second part of it is we will accelerate standard numerical procedures, like the things we learn in any of our standard numerical methods course, things like numerical solution of linear equations, ODEs, PDEs, and things like that. We will see how we can accelerate those calculations using parallelization on CPUs, GPUs. And then we will try to solve certain physics and engineering problems using these procedures. Things like solving an ODE can be used in a lot of engineering problems, lot of physics problems, so on and so forth. These are the primary objectives of our course. And what I expect as an outcome is at the end, you should be able to accelerate your own research work / applications for execution on multi-core CPUs and GPUs. That is the whole outcome of this course, that you should be able to do it for your own applications. Some modalities for this, I aim to keep this very beginner friendly. We will start from the basics. As you must have seen on the course webpage, the first week is dedicated towards the basics of parallelization. And I don't expect you to know any parallel or GPU programming. but I do expect you to know some basic C and C++ programming. The other thing is, a lot of you might be using Fortran for all your simulation purposes. While I will be giving examples using C or C++, these concepts discussed here carry over to Fortran with just certain syntactical changes. I will use the Linux operating system for demonstration later in the course, but the same concepts apply across other operating systems as well. And as I mentioned earlier, it will be primarily application based, that we will take applications from numerical methods, physics, and engineering problems, so that you get a feel of how you can tackle your own problems in your own research area or work. Sorry. Okay, so the agenda for this week is, and today is, introduction to parallelization. And we will look at the basics of it so that everybody is on the same page. I expect some of you might be having some previous expertise on this, but I would request you to bear with us. You might learn something new and also give others the chance to know something about this topic. Okay, so what is the whole point of this? The point of this right now is to see how we can have the faster execution of our code. So there can be two ways if you think about it. The first way would be to execute things faster in serial. The other way would be to execute multiple things in parallel. What do I mean by this? Let's say we have a task. Let's look at the first row, the one which I have mentioned as task. Let's say this is one, the colored boxes represent individual tasks which has to be completed to perform one job. Let's say we are doing something, I'll take an example of preparing a 4-course meal. So let's say to prepare the 4-course meal, you have to first, let's say the first two things represent the first item, the second two things represent the second item, the third two things represent that, and the last two represent the fourth meal item. So what are the two ways? One way is to do one thing faster than previous. Let's say we are executing such a task on one core. If we have a faster core, we can take lesser time for each task so that the total time taken is very less. But what we see here is the sequence of events remain the same. The other way to do it could be if you have multiple cores in your system. That way, let's say the example I have given here is we have 4 cores. That way, you can do 2 work in parallel and spread it over 4 cores so that you can have even shorter execution time. While doing this, there is an inherent assumption in the layout of the problem. Can somebody guess what? Like in this figure, while we are going to the method 2 and having 4 cores of execution, and we are doing 2 units of work in parallel, so that we have a shorter time of execution. What is the inherent assumption in this? Can anybody guess?
That each task is independent of each other.
Yes, correct. So as I took the example of making a 4-course meal or something, let's say you have to buy something, let's say that be the first purple box and red is the cooking part. You cannot start cooking before buying, right? So that part has to be done in serial. But then let's say there are 4 different items you want to make. Yellow is the point of buying something, green is the point of cooking something. So you can buy parallelly and cook parallelly, but you cannot cook before buying. So you have to see which part of your work is parallelizable. So that way, in the 4-course example, the method 2 which I have shown, you see that I have maintained that order, that the red comes after purple, this color comes before this, the dark black, gray comes before blue, and the green comes before yellow. That sequence has to be maintained, but because that is inherently a serial task, but then you have chunks of serial tasks which can be computed in parallel. So this is the other way in which we can do it faster. So that typically requires even lesser time, and it is dependent on the number of cores you have in your system. Yeah, good. So there are certain problems. So as I said, the method 1 is going for a faster processing using a single core. So that is like doing one thing faster. In computer terms, how can that be done? You have to increase the clock frequency. The frequency at which your CPU runs, that is your clock frequency. Nowadays it is 4 gigahertz, 4.5 gigahertz, so on and so forth. You can start to increase that. There are other small technical things like pipelining and other things like improving compilers. So what is pipelining? Computer instructions are generally made of 4 different parts like fetch, decode, execute, write. Each command you give can be again divided into 4 different parts like this. If it is not pipelined, first you fetch the first instruction, then you decode it, then you execute it, and then you write it. Then you go for the second instruction. What happens is you see that once fetch of 1 is done, the fetch module is waiting for the instruction 1's write to finish. There is no need to do that. You can then start fetching the instruction 2 fetch part, and then everything falls into place. For 3, you do the decode next, so on and so forth. This is sort of parallelization, and it is called pipelining, so that you different instructions, part of each different instruction can be executed at the same time, so that there is proper utilization of all the parts of the CPU. The other part is, as I said, we can start increasing the frequency, like how quickly you are doing that. So this graph on the right hand side shows the I think it's the average or the highest clock frequency of different companies like AMD, Intel, things like that, and how that frequency has increased over time. So if you look at 1970s, it is quite low, around 1 megahertz and things like that, 1975. And there was a sharp increase, almost a linear, not a linear, quite a sharp increase over the time from 1980 to around 2005. And after that, you can see that that thing has stagnated. So there is a reason for that. So what you are seeing is we have not been able to keep increasing the clock frequency, which was our medicine for having faster execution. That is not possible right now anymore. The frequencies have stagnated. So why is this happening? So this is related to a bit of what is happening inside a computer. So every transistor which are used in a CPU, they are MOSFETs in a logic circuit, and our binary which is stored in CPU and which is processed, that requires switching of those transistors in a logic circuit. And every switching consumes power. That power required is dependent on the omega is the frequency, capacitance, and the voltage. You see, it is proportional to the frequency. So if you keep on increasing that frequency, what will happen is the required power for that type of a switching will keep on increasing. Therefore, power budget becomes an issue, that how much power you can dissipate from your CPU. And I think all of us know that, like, right now you need very proper coolers to run your computer. And it is very difficult. Like, some machines can consume upwards of 200 watts on just the CPU. Yeah, so this formula has been taken from this reference. So the issue is we run into a power wall, that we cannot just keep increasing the power so that we can keep increasing the frequency. So this says that we just cannot keep on increasing the clock frequency. And this is primarily the reason why this has been saturating. So what now? What has happened is there is something, this graph, if you look at it, there are multiple data points. You see on the top part, there is this orange, which is called the transistors count. That is increasing almost linearly. No, that is also increasing exponentially, because y-axis is on the log scale. If you look at the frequency again, you see that there has been an increase, but then it has again stagnated. That correlates pretty well with the typical power which has been dissipated through the system. That has also stagnated, because we cannot go to more than 10 to the power 2 or something like that. And the number of logical cores which is there in the system, that has been 10 to the power 0 till sometime after 2000, and after that we have started seeing multi-core. So what does this entail? Like, what does this mean? There is something like this graph of the number of transistors in our CPU, this has been something called the Moore's law, which is the observation that the number of transistors on an integrated circuit will almost double every 2 years. This is not a law per se. This is sort of a trend which has been the guiding principle for the semiconductor industry. Like this has been seen empirically, the Moore's law. So what we have is more transistors every 2 years, 3 years. So with time, you can pack more and more transistors. But you cannot keep on increasing frequency due to the power budget. You cannot dissipate that amount of power. Therefore, you cannot increase frequency so much. So we have more transistors available to us. That means we can have more individual processors in a single package without increasing the frequency of those individual processors. Therefore, now it has become that we must parallelize to obtain performance rather than trying to going on increasing the frequency of each core. So this is the situation right now. So multi-core, like this has given rise to the multi-core processors. Like if we look at Intel processors, for example, we have 60 core, 56 core, and these are all recent processors launched. So I think the highest right now is 60 cores on the Intel side. You can see that the maximum frequency is 3.5 on the right hand side of that. But you can see if you have lower core processors, like what you have in, let's say an i7 or a i5, they will have 8 cores or 10 cores, something like that. Though their clock frequencies are way higher. So there has been a sort of a balance, like you will get 60 cores, but you will have a little bit less amount of turbo frequency. So there has been, so these are all server CPUs, Xeon platform CPUs. So these are used in servers where there is a necessary for a large number of cores for our workloads. If you look at AMD, they are also following the same trend. They have all their 64 core and 32 core and 48 core CPUs. And if you look at the boost clock rate on the right hand side, you will see as the number of cores reduce, there is a certain uptick in the frequency. See, the highest has 64 cores, but its boost clock is around 3.5 gigahertz. If you go down around 16 cores or something like 24 cores, you will see that their boost clocks are around 4 gigahertz. So there has to be a striking balance between these two things. Yeah. Again, those are all x86 stuff. On the ARM side also, we are having multi-core CPUs. Apple launched their M3 series recently. They have 12-core CPUs, 14-core CPUs. Snapdragon launched their Elite X very recently. It has 12 cores, each going up to 3.8 gigahertz. There is this ARM vendor called Ampere, who is now giving, sorry, let me admit just a few people. Yeah. So Ampere, who have, there's an ARM company, ARM CPUs, they give around 32 to 128 cores per CPU. And also NVIDIA is also trying to create CPUs of their own. They have brought out this architecture called the Grace Hopper Superchip, which joins a GPU and a CPU together. And that you can also see the number of CPUs on that is 72. So you have a tendency of creating CPUs with larger and larger number of cores. Okay, so let's say you have a laptop you are joining this meeting from, or you have a desktop. How would you find the number of cores? If you are on Linux, the command would be lscpu. You might use it and find out the number of cores. For my system, I have run the command and I have 12 CPU cores. Basically, I have 12 cores and each core can run 2 threads. That gives me 12. So I technically have 6 cores, but the number of logical cores is, because I have multi-threading enabled, that is times 2. That gives me 12. So you can try this out in your machine later on if you have a Linux machine. For any Windows machine, you can try, I think you can find it in Task Manager, how many cores and how many threads you have. Okay, now like what we saw here, if we just go back a few slides, if we had 4 cores and a larger number of tasks, and let's say each of these individual tasks is also independent. If we had 8 cores, we could have done it in a smaller amount of time, right? So does that mean if we have more number of cores, does it imply better performance. So the question is, should we keep on increasing the number of cores in our system? Here comes the fact that we should not. What that is governed by something called Amdahl's law. Let's say that we have one task which has some serial part, because as we discussed before, not every job will be fully parallel. Some jobs will have a serial part and some parallel part, things which must be done serially and things which can be done parallelly. Okay, let's say we are executing that on a single core system, and let's say the serial part takes T1 time and the parallel part, which can be parallelized if executed on serial, takes T2 time. Therefore, now if we execute this same code on a system with n cores, we will have the serial part won't be affected, because if the problem is inherently serial, we cannot parallelize it. It is equivalent to running it on one core. So that time won't change. That T1 remains as T1. What is affected is the parallel time. If it is originally taking T2 time, and if I can parallelize it properly across n cores, it will take T2 by n. This is okay, right? So it will take T2 by n amount of time, which you can see from the graph that since that part is reducing, the total time taken is lesser. So we can compare what is called the speed up. Like when executing on n cores, we can find what is the speed up. Speed up is defined as what was the original time taken, that is T1 plus T2, and what is the time taken after parallelization on n cores. Again, as I said, the serial part is not affected. What is affected is the parallel part. So T2 becomes T2 by n. We can define a ratio, T2 over T1, the ratio of amount of parallel time by serial time, as P, and therefore the formula becomes 1 plus P by 1 plus P over n. Can somebody tell me what happens if n becomes very large?
Only the T1 remains and T2 disappears.
I mean, no, I mean, it becomes probably 1 plus P, right? If you put n as very large, it becomes 1 plus P, isn't it? Yeah. So what we find is the speed up becomes a constant and it becomes 1 plus P. So it is limited by the amount of parallel tasks you have in your computer, in your problem. So it is not like that if you keep on increasing your number of cores in the system and you try to run your program on it, that the speed up will keep increasing by a factor of n. So what happens is after increasing it to a certain time, it becomes limited by the amount of serial portion of the work which is there. So if you plot S as a function of n for different values of P, it looks like this, that there is a sharp increase in speed up for small values of n, but then it saturates out for larger and larger values of n. So from this figure, what I mean to say is, let's say you have a problem which has a p-value of 1, that you have equal part serial and equal part parallel portion in the problem. There is no point of you running this problem on 400 cores. You could have very well run it on 200 cores and get almost the same performance. You can see the graph, the speed up is almost 2. So for different values of P, you get different curves, and what you see is if you increase the amount of parallel portion of the code, let's say another problem has twice the parallel portion compared to the serial portion, you will get more speed up. The maximum speed up will be 3. So you have to see like which value of processors is optimal for your execution. There is no point increasing number of cores available in your problem to 1000, 2000 without doing this sort of a study. Again, this is ideal behavior. This is assuming, this is again an ideal scenario, which I have shown here in case of Amdahl's law. A large n might cause, it has been seen experimentally, like if you run your problem on current systems, that it might cause a decrease in S. Can somebody guess why?
Because of communication bottleneck?
Correct. So over here, we have ignored what he is saying, communication bottlenecks. And also not only communication, launching that many threads and everything on a system, that also has an initialization cost. Launching 500 threads and 5 threads will take different times. And again, communication bottlenecks also come in. If you are going to communicate between 500 processes, that will take a lot of time compared to if you are going to communicate between 5. So there has to, again, it becomes a question of balance, that how much speed up you are getting, how much time you are losing in communication, and how much parallel program you have, such that there is a balance between all three. So this is the ideal behavior. If we do this actually on using some algorithm on some processor, on some machine having huge number of processors, you will see that this line is not straight like this. After becoming saturated, it starts to drop off. Yeah. So this Y is due to communication bottlenecks. Okay. So till now we have looked into the more or less this part of the thing where we motivate the need for parallelization. We now have to look into what hardware we have available. But before I go into this, till this part, anyone has any questions? I would take questions now. So Swarnim is asking, isn't Moore's law now broken due to quantum mechanics? Yes, I mean, this is at the cutting edge. So you are right, sort of, because I think recently only Apple launched their CPU using 3 nanometers. There is a limit to which you can pack more and more transistors. So what happens is you have a fixed size. You cannot make bigger and bigger CPUs. So you have a fixed size. So now to pack more and more transistors, you have to make those each transistor smaller and smaller. So what happens then is, right now, I think the state of the art is 3 nanometers. Now, if you reduce even more, I think Swarnim is correct what he is saying, that you will now start getting so small transistors that they won't function properly due to this quantum effects. But I think they are trying to go to 3 nanometers they have launched, I have seen. So I think they can reduce it further, but that is, I think we will survive for a few more years, maybe. Okay. What if we use a combination of one for series and multiple for parallel? Siddharth is saying. What do you mean by that? Can you explain? Combination of one for series and multiple for parallel?
So if we use one processor for series and the multiple means parallel processing for the parallel part.
Yeah, but then it's like saying that you cannot use, when you are having a parallel processor, that can execute a series task, right? So we don't specifically need to have a series processor, like in serial processor, which is specifically made for serial execution. Your parallel processors, what you have in your desktop and this thing, in your laptops, they have multiple cores, and their cores are very fast. As I said, current i7 or i9 processors, they are executing at around 5 gigahertz, 6 gigahertz, and so on. So they are quite fast in respect to serial calculation. And they already have 10 cores, 12 cores, 16 cores. So you can use them for sufficient amount of parallelization also. But then where your point becomes true is, as I showed you the graph in, like, for the AMD or Intel, as you see that, like, on, let's say, servers, you don't use servers for playing games. There are like different classes of tasks which benefit serial and which can benefit from multi-core. These are all generally server processors, and these you will not generally use for parallel tasks. So you are correct in the sense that all the CPUs you have in your laptop and desktop, they are optimized towards serial execution. Their clock speeds are quite high. But then what you have is, so what you have is, you will have also certain parallelization facilities like parallel cores built into it. But then the processors shown here, which has 60 cores, 56 cores, they are actually not optimized for serial execution. You can use them for serial execution, but they are not optimized. They are mainly used where you have a lot of parallel computation to be done. Okay, yeah. So Siddharth's point is fine. Anything else? Okay, we will go ahead. So we again now look into a bit of the hardware, like whatever hardware we have and how we can arrange them to form multi-core CPUs and G clusters. So in the previous slides, we have already looked into multi-core CPUs from Intel and AMD. The examples I gave you. So we define generally in HPC and parallelization domain, we define a single node as a self-contained computation unit, which contains CPUs, RAM, storage, GPUs, etc. What can be a node? Your workstation can be a node. Your laptop can be a node. These are all single unit self-contained units of computation, which has its own CPU, own RAM, own storage, and some other cards like GPUs. A node can have, let's say, more than one CPU. Generally, whatever you have in your laptop or your workstation, they have only one CPU, which can have multiple cores. But in certain expensive motherboards and systems, you can buy which has dual socket and in certain cases quad socket. Like in a single motherboard, you can fit 2 CPUs or even 4 CPUs. So why is this needed? As we saw, the maximum till now, the number of cores is around 60 or 64. So in a single machine, you can get at least 120 threads. But what if you need more? So these are the situations where you can buy a dual socket or a quad socket system. You can put 4 CPUs like that. Each can have, let's say, 60 or 30 cores, and you can end up with 120 cores and 240 threads, things like that. So you can have dual socket or quad socket systems. But this is quite rare and very expensive nowadays. And the support is very much vendor dependent. Like you cannot simply take one CPU and put it in this server socket and another one in another socket and expect it to run. It is very much vendor dependent, and you have to buy specific systems to get dual socket or quad socket support. What is the feature of this sort of a system? All the CPUs, let's say this system has 2 CPUs, this system has 4 CPUs, all of them can have direct access to your RAM. So you see in these pictures, there are the RAM slots beside each of these sockets, right? The black lines. These are the PCI slots, but these which are just beside the CPU, these are your RAM slots. You can put many RAM, like RAM sticks into it, and all the CPUs here have direct access to that memory. But again, it is not, let's say you have a CPU which is here, and if you have RAM here, the RAM controller, the memory controller is generally in the CPU nowadays. So this CPU will have direct access to this memory which is in this slot, and this direct access to this one. But this CPU will not. This CPU will have to go through an interconnect. So there is a connection between these two CPUs so that to the software, to the program you are writing, to Windows, to Linux, these two CPUs together appear logically as a single unit, but they are separate units at the hardware level. There is an interconnect between them, and this CPU can access memory connected to this CPU and vice versa. Same goes for the quad socket thing, but the access time is unequal. So this is called NUMA, non-uniform memory access model, which is generally used. So such a system, like you have a dual socket system or a quad socket system, is generally packed into a server node like this, which I was defining as a node. You will have, for example, this one has a AMD CPU packed into it. There is cooling made into it. There is some PCI slot in which you can put GPUs and everything. Okay, sorry, what happened? Yeah. So on and so forth. This is a rack server. This might as well been your workstation as well, where you can put multiple CPUs, GPUs, and this is a node. This is, for example, is a gigabyte hardware, which I am showing the picture of. This has cooling and everything built into it. Now what can be done is, let's say you have one such node and you can do, let's say you have a single CPU which has 60 processors. You can get at most 120 threads, and RAM will also be limited. You can see in this figure that there are 448 RAM slots. You can connect, let's say 32 GB RAM sticks and only get 32 into 4, whatever that is, that amount of RAM into it. But as you know, currently machine learning models, things like that, they take huge amount of data, and you have to store that on memory somehow, right? So a single node like this will not be enough in that case. So what do? We take several such nodes and connect them together. Why? As I said, since if you need access to more threads, more cores, more memory, more GPUs, things like that, that cannot be fit into a single node practically. So you have to connect multiple such nodes together. How? They are connected using fast networking, like high-speed Ethernet fiber and network switches. Why high speed is needed? Because while you are doing some calculation, you have to talk, each node has to talk to some other node, right? To share data between them, things like that. So at that point, high-speed Ethernet or fiber becomes very important. A typical such arrangement with multiple such nodes is generally called a rack, and many such racks can be connected together to form a cluster. So you guys might have seen in videos online or in your institutes, if you have a cluster, a rack which looks like this, where there are multiple nodes connected into it. The back view, if you look into it, you can see all the power, all the networking which is there. Generally, racks also have certain storage nodes, which is dedicated towards having storage in only storage. Certain nodes are optimized for only compute. Certain nodes are optimized for having only GPUs. And I think on the top, you can see there is a network switch as well. So this becomes a server rack, which has many such nodes packed into it. Sometimes that is also not enough. In that case, what you have to do is, you have to have such racks again connected together to form a cluster, a proper cluster. For example, the one on picture on the right I am showing, that is a cluster. The name of this cluster is Frontier, and it is made up of multiple such racks, which is connected again by some sort of fast networking. Do any one of you know what is special about Frontier? So Frontier is currently the world's fastest cluster. How do we know that? There is an organization, there is a website called Top 500, which lists the most powerful clusters and supercomputers in the world. They use something called the LINPACK benchmark. Like there is a set of tasks you have to do. That same set of... Sorry, are you spelling something? MM? Okay. So the LINPACK benchmark uses linear algebra tasks like solving equation and things like that. The same set of tasks each and every computer has to perform, and they have to report their performance. And that performance is used to make this list. It is called the LINPACK benchmark. So as of June 2023, this is the list, the first 5 supercomputers. As I said, Frontier is the largest and the most powerful one. It has this many number of cores. And next is Fugaku. Fugaku is special because if you see Frontier, it is using AMD CPUs, which is x86. Fugaku is special because they use ARM CPUs. I think Fugaku was holding the #1 position last year, before Frontier came online. And after that, you have Lumi, Leonardo, and Summit. I think Summit was the fastest few years ago. So this is the top 500 benchmark. Top 500 list, which is benchmarked using that Lynn Park benchmark. If you look at the power, if you see some 22,000 kilowatt, so you can imagine how powerful these machines are. In India, we have, I think, 4 or 5 entries in the top 500. So we have something at rank 75 at Airavat at CDAC. Param Siddhi, we again have at CDAC. Pratyush at rank 169, we have at Indian Institute of Tropical Meteorology. I think they do weather simulations in that system. And I think, again, we have in National Center for Medium Range Weather Forecasting, Mihir, that is at rank 316. So yeah, this is the position in which India is in the top 500. And for students, I think some of you are from IIT Madras. I am also from IIT Madras. We also have some cluster available to us here. It is named Aqua. We have around 11,680 cores. We have 30 GPUs. And our teraflops are peak performance max and performance peak is 734 and 1.106 teraflops. So you can compare. In terms of India only, we are still quite behind, but I think there are plans to upgrade. Yeah. So if you see in this picture, they have mentioned 30 GPUs. For example, this Param Siddhi, if you look into it, this is made up of NVIDIA DGX A100. This is a GPU. A100 is a GPU from NVIDIA. Again, I think all of these rank 1 to 5 systems, if you look at it, Frontier has AMD Instinct GPUs. So currently, a significant portion of computing power of these clusters and supercomputers come from GPUs. You cannot simply do it using CPUs. GPUs were originally designed for performing graphical calculations and rendering. I think most of us use GPUs for gaming, doing video editing and things like that. And this is what they are originally designed for. But right now, they are already being used for AI, high performance computing, and scientific computing. What is their characteristic feature? They have thousands of cores, but they are unlike CPU cores. Your CPU might have 12 cores, 18 cores, and your GPU might have some thousands of cores, but those two types of cores are unlike. They are not the same type of cores, and they have very fast memory. For example, what do I mean by fast memory? In your current workstation, you might have DDR4 memory, DDR5 memory if you have a recent machine. But then in GPUs, you have GDDR6, 6X, and even HBM, HBM2, HBM3 is coming out. Those are very high bandwidth memory, which allows rapid access to the data in that GPU memory. So GPU vendors are like NVIDIA, which has different classes of cards like GeForce, Quadro, Titan. GeForce is generally the gaming GPUs, which you have in your laptop or your desktop you used to play games. Quadro, Titan, and things like that. These are workstation cards, which are used for other applications like video rendering, video editing, and high performance computing. AMD also has similar things. They have the Radeon line for their gaming and Instinct. This is the recent lineup, which is used for HPC. You saw that is also within that Frontier system, that they are using Instinct AMD cards. Intel also has inbuilt graphics, like most of your laptops might have some Intel inbuilt graphics, and they have recently come out with ARC GPUs, which are discrete GPUs, not inbuilt into your CPU, which can be used for gaming and certain other computations. Phones also have GPUs. For example, all your phones which has Qualcomm CPUs like Snapdragon, they will generally have an Adreno GPU in it. So on and so forth. There are many other vendors, but these are the major players in this space. In this course, we'll be mostly using the NVIDIA stack. Like we'll use GPUs from NVIDIA and we will use software from NVIDIA. So that is the stack we'll be using primarily because they are the market leaders. Their software stack and hardware stack is very well developed and they have very nice support. So, and they have been used like CUDA and OpenACC, things which we will learn later. They are well developed, well documented, and used industry-wide. So these are some examples of GPUs from NVIDIA. So you have A100, A30, A10, and something called the A100 SXM. So this is PCIe. So we will come to this later, but there are many ways you can connect GPUs. One of the ways is through what is called a PCIe slot, and you can connect through, you have a something else called an XXM module. The GPUs we will be generally dealing with are generally PCIe. If you have a GPU in your desktop, it will generally be connected using the PCIe slot. And SXM modules are very costly, and they are generally reserved for supercomputers and clusters. I think A100 was the champion GPU from NVIDIA till a few years. I think recently H100 GPU has come out, which has succeeded this, but still A100 is quite a costly and powerful GPU. And I think you have A30, A10, which are smaller versions of the same thing. On the AMD side, as I said, Instinct GPUs, MI200 series is there. Again, you can have both PCIe and SXM, that sort of a connection, and they are also of similar performance. So if you want to find out what type of GPU you have, the way to find it out in Linux would be lspci. You open up the terminal, like to find out the CPU, you put lscpu, and for getting the GPU, you have to write lspci, put a pipe, grep NVIDIA. This is for NVIDIA GPUs only. And you will get an output like this. For example, I did it on my workstation. I have two 3090 GPUs connected to my workstation. And therefore, I get two VGA compatible controllers, which come up using the output of this command. You might have other GPUs, you might have AMD GPUs. So in that case, you just do lspci and look at the output. You will see that it should come up. If it is a PCIe card, it will come up. I am pretty sure it will mostly be a PCIe card, and it will come out in that output. Okay, now we discussed about CPUs, multi-core CPUs, how many cores they have, things like that. We discussed about GPUs, why they are used, where they are used, so on and so forth. There are even further other types of HPC hardware which are used. There are certain things called FPGAs. What are FPGAs? FPGAs are called field programmable gate arrays. What are those? So if you think about a CPU or a GPU, you generally have what is called, their function is pretty much fixed. As in they have inbuilt adders, some logic circuit. Their function is pretty much fixed. You can modify their function somewhat. You can do certain operations using those fixed function objects. You have adders, things like multipliers, and so on and so forth, other execution units. Similarly for GPUs. But what are FPGAs? FPGAs are field programmable, that you have a series of gates, an array of gates, and these are field programmable so that you can build specific hardware. Let's say you want to do a very specific application, like let's say doing a matrix multiplication. You can take this FPGA and using software change the inherent structure of that electronic circuit so that it is now specifically made for doing matrix multiplication. Once you are done using that application and you want to do something else, you can then change back and put some other description into it, and you can use the same hardware for something else. So there it comes the fact that it is called field programmable, that in the field, while you are using it, you can program it. You can change the circuitry inside it so that using software, so that it can represent different hardware components, which in case of CPUs and GPUs is mostly fixed. There are other things like DPUs, which are used for data processing and fast networking. Right now in the age of ML and AI, we have a lot of data being generated in different softwares and things like that. And you have to process that. And also networking has to be very fast. So in that field, DPU comes into play. You can have an NPU. Okay, let me see what questions are there. First 1 second. I think Khatri Ashok has asked NVLink versus PCIe. And Kuldeep is asking about TPUs, tensor processing unit, and GPUs. Okay, I'll come to that. Let me finish this. Neural processing units. Again, I think that ties in pretty well with Kuldeep's question. TPU is a tensor processing unit. What is that? Let's say a GPU, what you have, GPU is made for computation of a certain type of algorithms, and you can use that for computing what is in machine learning algorithms. In machine learning algorithms, what are you essentially doing? You are essentially doing, I think, big matrix multiplications. You are doing linear algebra operations, and which are like very large linear algebra operations and matrix multiplications, right? So in that case, again, I think it is a specialized version. You can call it as a specialized version of a GPU, where it is hardware is made such that it is very much optimized for doing tensor and matrix operations. That is the essential difference between, let's say, a TPU and a GPU. A TPU is basically a tensor processing unit. I will include that maybe later in this slide as well for completion. Okay, so that maybe answers your question, Kuldeep, is it? Yeah, okay. On the similar vibe, a same thing is a neural processing unit. Again, they use the same thing for machine learning algorithms where you have to do large matrix operations. Matrices are generally tensors, and tensors you can do using TPUs as well. And you have something called ASICs. What are ASICs? ASICs are application-specific integrated circuits. What does it mean? It means that you will make an integrated circuit, an IC, for a very specific purpose, and it will be optimized for that purpose only. For example, the TPU Kuldeep mentioned, that can be thought of basically as an ASIC, like it is very specific application. You are using it for a for your machine learning algorithm, but then that is again a bit general. ASICs are generally made for exactly specific, like you will fully mention out what is the problem and how you have to solve it, and you make it into a circuit. So that is an application specific. Whatever application you have, you make a circuit for that, and you have something called an ASIC. So these are some of the things, like you have Altera and Stratix FPGAs. These are quite popular. NVIDIA themselves have a DPU called Bluefield. And this ASIC I was talking about, Mythic, there is a company called Mythic. They have made a chip which is made purely for matrix multiplication purposes. It cannot do anything else. This chip, Mythic, it looks like a CPU, but it is not a CPU at all. It is just a chip which is made specifically for doing matrix multiplication and nothing else. So this could be one of the examples of an ASIC. Any questions till now? Maybe somebody else, some questions? Okay. All right. So yeah. So this is all the hardware we have seen till now. I will also talk about some recent trends. This is a bit extra, but I think it is important. Why is it important? Like previously, let's say you have a laptop or a desktop. What you end up is you have a separate CPU, you have a separate GPU, your RAM is different, your security chip is different, your IO chip, input-output controller is different, your USB controller is different. Previously, and still now, architecture persists which looks like this, that every item is different and made by different companies. Intel makes your CPU, NVIDIA or AMD makes your GPU, Samsung or SK Hynix makes your RAM, and things like that. So what is the issue with this is, the issue becomes that there has to be communication between them. So there is some communication delay between every chip, and then there is a problem of integration. Like Intel will make chips to their own standard, AMD will make GPUs to their own standard, RAM will be made by Samsung to their own standard, and everything has to work together. What recent trends show that companies are moving towards something called a very tightly integrated architecture and coming out with SoCs, system on a chip. What is that? That is all what you can need from a computer. Let's say a computer is put into a single chip. So the diagram shown here is of the Apple M1 chip. I think you guys must have heard about this. So what it does, within a single chip, they have put a CPU, they have put all the memory, they have put all the GPU, they have put a separate neural engine, that NPU I was talking about, a separate neural engine, and this fabric is the interconnect. So there has to be some communication between CPU and GPU. This fabric, everything is put together in a single chip. And yeah, so what is the advantage of this? The advantage is the communication is very seamless. It is made by the same company, so they can tune their hardware to work properly with each other. The other benefit which is seen in this Apple M1 chip is their RAM access is common. We will come to memory access models later in the course, but what they have used is something called unified memory. So CPU and GPU can access the same RAM. So that is actually very useful. And neural engine can also access the same RAM. So you don't have to worry about memory issues between CPU and GPU and things like that. So this is the move towards a single SoC. And this has its advantages. NVIDIA is also doing the same thing. They have come up with two models, the Grace Hopper Super Chip, which is a CPU and a GPU on a single module, and some Grace CPU, which is again like a dual socket memory, a dual socket system, which has two big CPUs on the same thing. So this has been the recent push towards tightly integrated architecture, where in a single unit you have your CPU, GPU, memory, and everything. Yeah, so this has been the recent trend in hardware. So we will end here. It's almost 3 o'clock, and what we will do tomorrow is we will start to see how we can program parallel CPUs and GPUs, like the architectures we saw before, like GPUs like this, or some multi-core CPUs which we have seen in this racks and all, how we can address them, like how we can program them. Well and good buying and putting such systems, how we can programmatically access them. It is not like if you have a code you have written in C or Python and you just run it on a cluster and it will run across every core. It is not like that. You have to do something special for them, and we will see how we can do that. With this, I think we are out of time, and we will end here today. And if there are questions, I can take them. Okay, Pranod asks, do we need to install anything on our system? We will go through it. That will form a part of it on the second week. I will show you what you have to install and how you have to install it. So don't worry. Today and tomorrow's lecture, we don't have to install anything right now. Okay, Khatri says, I am curious about how multiple GPUs are interconnected. Okay, I think you have only previously asked about NVLink and a PCIe. So there are multiple ways you can do that. I'll come to Pranod's thing. WSL, okay, I'll see if it is possible, but I'll answer Khatri's question first. So NVLink is something like a interconnect between the GPUs. It is a standard made by NVIDIA in which you can directly connect the memory of two NVIDIA GPUs. If it is not that, you can directly have communication, like if you have 2 to 3, let's say I'll go back to one of these figures, like one of these pictures I have. Yeah. So if you see in this dual socket or quad socket motherboard, you can see multiple PCIe slots are there. So you can connect multiple GPUs directly in those PCIe slots, and there will be communication between those GPUs through the PCIe slots using the CPU as the staging. We will have small examples for this in our course, where we will just talk about how you can use multi-GPU systems. The system I have, the example I showed, that is also a system which has 2 GPUs. Let me show you it once. Yeah, you see, I have 2 GPUs in my system, 2 3090 GPUs. They are not connected using anything like NVLink. They are directly connected between them using only PCIe, and the communication between them is done via the CPU that way. Okay. Anything? Does this answer your question, Khatri?
Hello.
Yes.
Yeah, sir, I wanted to ask that if PCI is coming, that means the communication will happen through CPU. Is it
Yes.
that?
Yes, generally you will have to do it, but again, as you said, NVLink is there in which you can communicate directly between two GPUs. That is done probably using NVLink, but that is not there in, let's say, the gaming GPUs. You can do it using NVLink, but for basic purposes, I think communication via PCI is also fine.
Okay. Means if two GPUs directly want to connect, we have to do it with NVLink,
Yes, yes,
and
yes.
through CPU, PCI is already there.
Yeah.
Fine. Thank you.
Anyone, anything else? So next day, we will look at how you can program such CPUs and GPUs. We will talk about different programming models, what is shared, distributed, and heterogeneous models. And okay, so maybe we will join at 2 o'clock tomorrow. Okay, thank you everyone for joining.